700 million years after the Big Bang, a galaxy did something that, according to everything astronomers thought they understood about the early universe, should not have been possible. It formed. It built stars at a furious pace for somewhere between 30 and 90 million years, assembling a real, structured galaxy out of raw hydrogen gas in a fraction of the time such a thing was supposed to take. And then, just as abruptly, it stopped. Not slowed down, stopped. Every sign of active star formation shut off, almost like flipping a switch, leaving behind a compact, quiet, apparently finished galaxy at a moment in cosmic history when nearly everything else in the universe was still an all-you-can-eat buffet of raw material and runaway growth. Astronomers gave it a catalog name that sounds more like a parts number than a discovery: JADES GS 01QU. But the people who found it, a team from the University of Cambridge's Kavli Institute for Cosmology, it is, as of that publication, the oldest dead galaxy ever observed. And the researchers who found it have been very clear, in interview after interview, about one uncomfortable fact. They don't fully know how it happened. To find it at all, Lucer and his team had to push the James Webb Space Telescope's infrared instruments to their limit, peering through a thick veil of cosmic dust that would have hidden an object this old and this faint from almost any telescope built before it. That the discovery required Webb specifically, rather than any of its predecessors, is part of the story. Hubble, for all its achievements, simply wasn't built to see light this stretched, this faint, and within less than 2 years of beginning science operations, it had already found something that broke the standard timeline. To understand why a dead galaxy is even a strange idea, you have to understand what galaxies are normally doing at this point in cosmic history. Picture the early universe as a nursery still under construction. Gas, mostly hydrogen, left over from the Big Bang itself, is everywhere, drifting through space in enormous clouds. Gravity pulls that gas together into denser and denser clumps, and when those clumps get dense enough, nuclear fusion ignites and a star is born. A galaxy, at its simplest, is just a very large collection of that gas, slowly and continuously converting itself into stars, generation after generation, growing heavier and brighter as it goes. In the earliest few hundred million years after the Big Bang, this process should have barely gotten started. Galaxies were expected to be small, ragged and hungry, actively pulling in fresh gas and turning it into stars as fast as they could, with nothing yet mature enough to have finished the job. Astronomer Tobias Lucer, who led the team that found this galaxy, put it plainly: galaxies at this stage need a rich, constant supply of gas to keep forming stars, and the early universe had that supply in abundance. It's the cosmic equivalent of arriving at a buffet the moment the doors open, when every dish is fully stocked. Nobody expected anyone to already be finished eating. And yet, when the James Webb Space Telescope turned its infrared instruments toward this particular patch of sky, that's exactly what it found. A galaxy that had already finished. A galaxy that had built its stars in one short, ferocious burst, and then simply stopped, while the rest of the universe around it was still just getting started. Think about the sheer scale of what already finished means at this point in cosmic history. The universe at 700 million years old was roughly 5% of its current age. Proportionally, the equivalent of a person finishing an entire adult career and retiring before their 4th birthday. Galaxies at this stage are supposed to look scrappy and unfinished, still assembling themselves out of the raw material available to them. Finding one that had already burned through its formative burst and gone quiet isn't just an interesting data point. It's a direct challenge to the timeline every existing model of galaxy formation assumes. Here's where the discovery gets genuinely strange, and where the phrase unforming starts to make sense as a description, rather than just a dramatic headline. Astronomers have a technical word for what happened to this galaxy: quenching. It describes the process by which a galaxy that was actively forming stars stops doing so, usually because something either removes its remaining gas or heats that gas up so much that it can no longer collapse into new stars. Quenching itself isn't new to astronomy. Plenty of galaxies in the more recent universe are quenched, including many of the largest, oldest galaxies we can see relatively nearby. What was new, and what made this particular discovery so unsettling to the researchers who found it, was the timing. Until this galaxy turned up, astronomers generally expected quenching to be a late-life event, something that happens to galaxies after they've had billions of years to grow, mature, and use up their fuel, the way a fire eventually burns through its wood. Finding a quenched galaxy at 700 million years old is a little like finding a fully grown, retired adult in a nursery that opened yesterday. The math doesn't work. There hasn't been enough time, according to the standard models, for a galaxy to form this quickly, run through an entire life cycle of star formation, and then shut it all down, all within less time than it takes light from some nearby stars to cross an ordinary galaxy several times over. Study co-author Francesco D'Eugenio summed up the puzzle directly. In the normal expected timeline of the universe, galaxies stop forming stars later, not this early. Whatever process caused this particular galaxy to unform, to go from a burst of intense growth to complete stillness, did it on a timescale that current theory simply doesn't have room for. For comparison, most of the other quenched galaxies astronomers had documented before this discovery were found when the universe was around 3 billion years old, roughly 4 times its age at the moment this one had already gone dark. That gap alone is what turned a single unusual observation into a genuine puzzle for the entire field. Let's pause and lay out exactly what the Webb data shows, because the details matter more than the headline. The galaxy formed the bulk of its stars during a window somewhere between 30 and 90 million years long, a blink of an eye, cosmically speaking, but long enough to build a real structured system. Then, star formation didn't taper off. It shut down rapidly, leaving behind a compact galaxy, notably smaller and lighter than most other quenched galaxies found at later points in cosmic history. And unlike some other quenched systems, this one shows no immediate, obvious culprit sitting in plain sight, no dominant blazing quasar, no unmistakable signature of a supermassive black hole clearing everything out, at least not one the data conclusively points to yet. That absence of an obvious cause is precisely why lead researcher Roberto Maiolino has been candid about the limits of current theory. Astronomers do have a short list of mechanisms that are known to quench galaxies elsewhere in the universe. A supermassive black hole at a galaxy's center can flare up, blast out enormous amounts of radiation, and heat or blow away the surrounding gas before it has a chance to collapse into new stars. A process seen clearly in other early massive galaxies, including one called GS9209, found by a separate team and quenched by an actively feeding black hole roughly 1 billion times the mass of the Sun. Turbulence and stellar winds from the star-forming burst itself can do something similar on a smaller scale, blowing gas out of a galaxy from the inside. Or, more simply, a galaxy's surroundings might just fail to resupply it with fresh gas quickly enough to keep the fire burning. Maiolino's team looked at all of these familiar explanations, and, in his own words, isn't sure any of them fully accounts for what Webb actually observed. That's a remarkable thing for a scientist to say about a well-documented phenomenon. It isn't that quenching itself is mysterious, it's that this particular galaxy quenched too early, too fast, and too cleanly for the standard toolkit of explanations to click neatly into place. This isn't an isolated oddity either, which is part of why the discovery has rattled more than one research group. A separate team, led by astronomers at the University of Geneva, using Webb's Rubies observation program, found another galaxy that had already stopped forming stars at an equally startling early point in cosmic history. A record-breaking case that deepened, in the researcher's own description, the tension between theoretical models of galaxy evolution and what Webb is actually seeing in the sky. And a third team, examining a galaxy called GS9209, found that it had built roughly 40 billion solar masses worth of stars, comparable to the entire Milky Way, in just a 200 million year window, only about 600 million years after the Big Bang, before a rapidly feeding black hole appears to have shut the whole process down. Taken together, these discoveries are sketching a pattern that theoretical models built before Webb's launch simply didn't predict. A subset of galaxies in the very early universe that grow explosively fast, build an enormous amount of mass in a geological eye blink, and then go quiet, all well within the first billion years of cosmic time. Astronomer Mauro Giavalisco, commenting on one of these findings without being directly involved in the research, called the pattern a remarkable discovery precisely because it forces the field to ask a harder question. Under what conditions does quenching become a widespread phenomenon this early, rather than the rare late-life event it was long assumed to be? It's worth being precise about what these Webb observations do and don't establish, because it doesn't make sense is a strong claim, and it deserves an equally careful caveat. What's established? This is a real, published, peer-reviewed detection. The spectroscopic data, the light broken down by wavelength, which lets astronomers read a galaxy's star formation history the way a chemist reads a spectral fingerprint, clearly shows an intense burst of star formation followed by an abrupt halt, all at a redshift corresponding to roughly 700 million years after the Big Bang. That timing and that abruptness are not in serious dispute. What's genuinely uncertain is the mechanism, and the researchers have been unusually open about not knowing the answer yet. Eugenio has raised the possibility that some of these early dead galaxies might not stay dead, that they could burst back to life later, resuming star formation after an unexplained dormant period, the way a wildfire can smolder and then flare up again given the right conditions. That would be a strange twist on the word quenched, implying not an ending but a pause. Other research on more recent quenched galaxies, observed when the universe was around 3 billion years old, found that these dormant systems generally don't reignite even when they merge with neighboring galaxies. The merger just puffs them up rather than restarting their stellar furnace. Whether that same rule applies to a galaxy quenched this early, at 700 million years, is simply not known yet. It's also worth being clear that doesn't make sense, doesn't mean physics is broken. It means the specific models astronomers built to describe how galaxies typically grow, feed, and shut down. Models largely calibrated using galaxies much closer to us in cosmic's time. Don't yet have a clean explanation for a system this young behaving this way. Maialino's own conclusion was measured, not alarmist. These models, built on assumptions from the modern universe, may need to be revisited. That's a call for better theory, not a crisis for the field. Which brings the story back to what Webb actually caught in the act. For most of the history of observational astronomy, a discovery like this would have taken far longer to confirm. Ground-based telescopes, even the largest ones on Earth, would have needed a month or more of dedicated observing time to gather light this faint from an object, this distant and this old. James Webb, with its far greater sensitivity to infrared light, the wavelength that visible, light gets stretched into after traveling across billions of years of an expanding universe, can pull in the same signal in a matter of hours. That leap in capability is precisely why these discoveries are stacking up so quickly. One record-breaking, dead galaxy after another, each one pushing the boundary of how early quenching can happen a little further back toward the beginning of time itself. Lucer's own description of the discovery captures the strangeness better than any technical summary could. Everything, he said, seems to happen faster and more dramatically in the early universe, and that apparently includes the transition from vigorous, explosive star formation to complete stillness. A galaxy that, by every existing model, should still have been in its infancy, had already lived an entire life and gone quiet, all within the first 5% of the universe's current age. Nobody currently knows for certain why. It might be a supermassive black hole feeding faster and more violently than current models assume young black holes can. It might be a surrounding environment too gas-poor to keep the fire fed. It might be some combination of mechanisms nobody has fully mapped out yet, unique to conditions in the universe's first billion years that simply don't exist anymore. Or it might be something Webb hasn't shown astronomers yet. A piece of the picture still hiding in data nobody has fully analyzed. What is certain is this: the universe's very first galaxies were not supposed to be finishing their life cycles this early. Webb found one that had. And until astronomers figure out exactly how, doesn't make sense isn't hype. It's the honest, working description of where the science currently stands. So here's the question worth sitting with. If the earliest galaxies in the universe can grow up, burn out, and go silent within a few 100 million years, faster than current physics can fully explain, how many more of these premature endings are sitting in Webb's data right now, waiting to be found? Lucer's team has already said they intend to keep searching for more examples like this one, precisely because a single data point can be dismissed as a fluke, while a pattern cannot. Every additional dead galaxy found at this early an age makes it a little harder to explain this one away, and a little more urgent to figure out what exactly the early universe was doing that the textbooks never predicted.